Alright, so we have Griffiths Electrodynamics, problem 3.15. What we're dealing with here is an infinitely long rectangular tube. Alright, and it's infinitely long in the z direction. Alright, but there's no variation in the z direction. So essentially this is a two-dimensional problem. So we'll be focusing on this picture here, where this is the cross-section of this rectangular pipe. Alright, I drew this, this side in a different color because these three sides are grounded, that is, they are held at a potential of 0, and this side is held at a different potential. In fact, it's not even a constant potential necessarily, right? It's a function of y. So it could be held, this potential could vary as you go up along this side. Let me go ahead and color in this side of our infinite box representation just so you can kind of see what we're looking at here. So again, we'll be working in 2 dimensions. This is a 2-dimensional problem, and focusing on the x and y direction. So this is a rectangular pipe with a height in the y direction of a and a width in the x direction of b. So in general, if we, let's see, we would be looking at Laplace's equation, right? There are no charges inside this box, so we have our Laplacian of our potential is equal to 0. 0 because there are no charges, otherwise we'd get Poisson's equation. And to write this in our 2-dimensional case, what this looks like is we have the second derivative with respect to x v plus the second derivative with respect to y. Alright, so that's the Laplacian written out in these Cartesian coordinates and equal to 0. We're going to use separation of variables, so that we can do this because of the linearity of electrostatics, right? So I'm going to write this v as a product of 2 functions, one we call x and one we call y. This is big X and big Y, where x is only a function of x and y is only a function of y. Alright, so now when we take the Laplacian of this, I'll just write these as primes. We get x double prime, taking the second derivative with respect to x, and then multiplied by y. There's, y does not depend on x, so we just write y. And then plus, now we have an x, and we're taking the second derivative with respect to y. So we get an x, y double prime. This is still equal to 0. Alright, so what we're going to do now is divide both sides of this equation by xy. Divided by xy, this side's still 0, obviously. So what we end up with is x double prime over x plus y double prime over y is equal to 0. So this tells us that x double prime over x is equal to minus y double prime over y. Now, since this side only depends on x and this side only depends on y, and yet they're equal to each other, the only way for this to happen is for these to both be equal to the same constant. So let me see. For now, I'm just going to write k squared. and then we'll figure out whether there's a minus sign here. And we'll talk about how we decide. So the reason they're equal to a constant is because if this is only a function of x, and if I can change, so this is only a function of x, this is only a function of y, and if I change x, well, if this wasn't a constant, this would be changing, but this is not a function of x, so there would be no way for this to change in order to stay matched up with this one. So that's why, in order for this to be true, they both have to be equal to a constant. All right, so this constant we're going to be calling k squared. And so yeah, let's look at our equations real quick, because what we want to do is decide whether there is a minus sign in here. Okay, so let me write out each of these equations separately, just as they are written right now. So I have an x prime prime, and then multiplying, so ignoring this middle part, multiplying both sides by x. We have, I'm going to include this minus sign for the moment, in parentheses still. This, and then y prime prime I'm going to divide both sides by this negative and put a plus sign in parentheses. I hope this doesn't get too confusing. But the real question is, if there's a minus sign here, there has to be a plus sign here, or vice versa. We know these are both equal to a constant, but we need to figure out whether that constant is positive or negative. The way we decide on that is our boundary conditions right here. So I'm just going to, looking at the solutions here, if these are basically the same equation except for this sign, right? This equation will either give us, if we have a minus sign here, we will get sines and cosines for our solution, and if we have a plus sign here, we'll get an exponential that increases as well as an exponential that decays. And so these are just things, you can solve this by proposing a solution and checking it, but it's good to just memorize this. Just know this. Know when you see this equation that you'll either get the exponentials or the sines and cosines. So which one do we want? Well, I'm going to cut to the chase here and tell you that if we have two sides that are 0 here on the boundary, then we need to use the trigonometric function. Why is that? Well, if you pick the wrong one and you decide that you're going to use the exponentials, e to the something, and then multiplied by constant plus e to the minus something multiplied by constant, that's basically a hyperbolic cosine. Is that right? Hyperbolic cosine. Yeah, so, and that does not equal 0, right? Hyperbolic cosine, I think, just, it kind of looks like a parabola, sort of like that. So that doesn't equal 0. So basically your solution, it will all have to go to 0. So that is a solution, except when you have these two boundary conditions, it will be forced to 0 across the whole thing. Maybe, anyway. Basically, what we have to do is, when we have these two conditions, when it's 0 on two boundaries, we're going to use our trigonometric functions. All right, I hope I didn't, anyway, if you don't believe me, just try the exponentials and see what you get. You'll see that you'll just end up with a mess and it won't work out. So we want, because this is in the y direction, we want our trigonometric functions to be in the y direction. That tells me, remember the minus sign gives us the trigonometric functions, and we want that in the y direction. So I picked wrong, okay? So this needs to be a minus sign. All right. And that tells me that this one has to be a plus sign. Well, let me just cross this whole thing out. It's just implied a plus right here. That also tells me that I got it wrong up here. All right, but that's how we decide which one is which, is based on our boundary conditions. Why can we use complex exponentials in the x direction? It's because this side is not equal to 0. If all four sides were grounded, then the complex exponentials would work because this Laplace's equation would tell us that the potential is 0 everywhere inside the cross-section of this tube. So it still works, but it's 0, so not very interesting. All right, so looking at what we've got now, what we have are complex exponentials for x. So let's write out the solution to this equation. X is equal to, for now I'm just going to call this ax, and sorry, I don't know if I said complex exponentials, I just meant real exponentials. Ax e to the kx. This time, this is a small x, right, variable x, whereas this is a big X, which is our function x that we had up here. And then we have our decaying exponential. All right, and for this solution, again, this is big Y and big X on this side. We have an AY sine of kx plus a by cosine of kx. All right. So these are the forms of our solutions. Again, in general, the most general solution that we can find. Let's write it out really quick. I'll just say most general solution. All right, V is equal to x, y, right? What we set up here, and that's equal to these two pieces multiplied together. But it's not only maybe I should have used different subscripts. Let's go ahead and change those real quick. So I'm going to change this to n's and this to m's. Well, never mind. Let's call them both n. No, we can't, because that would be the same as that. All right. Our most general solution is not just this equation, but any equation and these k's can be different too. Oh my goodness, what a mess, right? But this is what we get when we're doing partial differential equations. We don't just get nice simple solutions like this, like we would get for ordinary differential equations. We actually get an infinite sum of all the solutions for the ordinary differential equation. What a huge mess, right? So n equals 1 to infinity of a n e to the k n x plus b n e to the minus k n x. All right, this is our x function right here, and the y function is similar. We have, this time I'm going to use m, and now we have an am. These coefficients can be different, right? So we're keeping this completely general. Kmx plus a b sub m cosine k m x. And then I'll draw my little bracket out there. Okay. So if I haven't messed anything up already, here's our x part, here's our y part. Oh, I did mess something up, didn't I? This, these depend on y. Oh my goodness. Yeah. Right, yeah, remember y, the big Y is a function of y. What a huge mess. Alright, but we'll be seeing this so much that it'll all get worked out. So here's our y part, here's our x part, and and all this infinite sum multiplied by this infinite sum gives us our most general solution. But we can do better than that because we have our boundary conditions. So now we're going to start plugging in boundary conditions, and we'll see that a lot of these coefficients and things will start going to 0, which is nice. That's what we want. So first, let's go ahead and look at the y direction. We have to have things go to 0 at y equals 0 and y equals a. So looking here at our y direction, so at y equals 0, this part already goes to 0, right? Because sine of 0 is 0, so we don't have to worry about that. We'll worry about it in a moment. Cosine goes to 1 though, so that means in order for this piece to be 0, b sub m has to be equal to 0. So let's write out our boundary condition that we're using. V at y equals 0 equals 0. So what that is, what that is saying is that this bottom side right here is equal to 0. It's grounded, right? These are all connected. It's grounded. It's equal to 0. This is the boundary condition, and that tells us that all of these b sub m's, all the way from 1 to infinity, are all equal to 0. B sub m is equal to 0, all of them, from m1 equals 1 out to infinity. All right. Let's look at another boundary condition with y. V at y equals, now we're looking up at the top face right here, at y equals a. That is also equal to 0. Okay, so looking here again at our y piece, all these cosines are gone. In fact, this is no longer the most general solution because I'm going to cross this out, right? We killed that term when all these b's goes to 0. Now, this will tell us in order for sine to go to 0 at a, that happens every time this k is equal to n times pi divided by a. So this unfortunately doesn't tell us what a sub m is, but it tells us what k sub m is. And I guess, you know what, these are actually the same k as well. So, you know, maybe I could have combined these and only used one index of n. And, we'll write it out again over and over, and we'll get it. We'll get it. So, I'm just gonna write k sub m equals k sub n, right? Because these both came from the same constant, the same k. N or m, either one, pi over a. All right, when you plug that in right here, and you plug in a for y, then you get a sine of n times pi, and sine goes to 0 at every integer multiple of pi. So then that will take care of this. So, so this other boundary condition helped us out a little bit too. All right, let's look at another boundary condition. This time we're going to go and look at x. V at x equals 0 is equal to 0. So now we are looking along this face right here, and it is also grounded. And so what can this tell us? Well, if we plug in x equals 0 into these exponentials, an exponential with 0 up in the exponent is just 1. So these will both go to 1. So that tells me that a sub n multiplied by 1 plus b sub n, again multiplied by 1, is equal to 0. Or in other words, let's write it this way, b sub n is equal to minus a sub n. All right. And finally, we have one more boundary condition over here on this side. V at this time we have x equal to b over here on this side is equal to not 0, but what we're calling v naught as a function of y. Just double check and make sure Griffiths yeah, he calls it v naught as a function of y. All right, so what can this tell us? Well, we already know wherever it is. So we know that b sub n is equal to minus a sub n. So let us factor this out. Yeah, let's write out a few more steps for this boundary condition. So we have an a sub n, e to the k sub n, and then for x, we're putting in b, right? And then for b sub n, we're putting in a minus a sub n, what we found already. E to the minus k sub n b. And this is equal to this v naught sub y. Is that correct? Okay, it's not quite right, because we still, if we're not up at the top or the bottom side, then the the y part does not go to 0, right? So it's not quite enough to just say that this by itself is equal to v naught sub y, right? We have to basically talk about all of these other parts too. So let's let me cross this out, and we'll start on another page, and we'll start moving from our general solution here. All right, let's write this out better, because again, with these k sub n's actually being equal to the k sub m's, these I should have written this as just one sum. So let's write out what we have. Okay, so we're not going to worry about the last boundary condition at this exact point. Let's first write in what we found already for our using our other boundary conditions. All right. So for the x part, we did find that that we had this a sub n is equal to the opposite of b sub n. So factoring that out, we get an e to the k n x minus e to the minus k n x. This is actually a hyperbolic sign, right? We'll we'll write it as that later. Well, it's 2 times a hyperbolic sine, but that 2 can be absorbed into this coefficient here, or divided out, whatever. Okay, so now looking at our second piece right here, we had this a sub m, which I hope this is not too bad, but I'm going to write this as an a sub n y, and this is an a sub n x. Okay, and then we had a sine of k sub n y. Okay, and we didn't have this cosine anymore because the b sub m's went to 0. Alright, so again, this is not counting our last boundary condition. So we've gone from the general case into a few of our boundary conditions are included in this, right? We got rid of the b sub m, and we were able to make this simplification and so forth. So one thing we're going to do is combine our coefficients into just one coefficient. That will make things simpler to write. Let's just call it a. Why not? A sub n. No, let's not call it a sub n. And let's not call it b. Let's just call it c, because I don't want it to get confused with the previous a sub n's and so forth. Alright, now we said this one could be a hyperbolic sine, and the 2 we can pull out of this coefficient. We have a k sub n x, and then we have a normal sine, k sub n y. Now remember that we do know what k sub n is. It is equal to n pi over a, which we found from one of our, from this boundary condition right here. Okay, so kind of making a mess of things, but I think we'll still get the answer in the end. Alright, so now that we have this form, let's go ahead. See, this includes the y and the x. Now we can go ahead and look at our last boundary condition. So what we've got is we need to plug in, let me write the whole BC thing. V at, now it's x equals b is equal to v naught, which is a function of y. Where are we now? We're looking at this boundary condition again, which is our final side here, this orange side. Okay, and so let's write this plugging in a b for the x. Hyperbolic sine and I'm doing plugging in b for the x here, and then it's multiplied by normal sine k sub n y. Alright, so now where are we at? We have our last boundary condition, and what we're looking for, right? We know what k sub n is. What we don't know is what c sub n is. So this is an infinite sum of these terms, and they are all separate and orthogonal and all that, and they each have this n dependence, and they each have a coefficient in front. We need to know how do we find those coefficients? How do we weight our average, or how do we weight our sum of these terms? So what we're actually solving for here is the C sub n. That's what we're using this final boundary condition for. So what we're going to do is Fourier's trick, where we are going to multiply both sides by a sine of a different k sub n, which we're just going to call it m, all right, even though we had that whole confusion with m in the past. We'll just call it m. So let's just write it out and maybe it'll make more sense. So I'm going to be integrating in the y direction, and we're only talking about from 0 to a. Okay, and I'm multiplying by sine. Let's not call it n or m. Sorry. Let's go ahead and put a prime on all of these components, or all of these everywhere we see an n. All right. It's just an index that we're using to sum. All right. Because I want to use n for the one that's going to be left over. If that makes any sense, I think. Anyway, we'll see how this works. So now we're using a k sub n, so without the prime. Okay, and we're integrating with respect to y. All right, so just to rehash, what I'm doing is I'm multiplying both sides of this equation right here by sine k sub n without the prime, multiplied by y, this right here, and then I'm integrating from 0 to a with respect to y. So this will also be an integral, 0 to a, all right? And again, these are the n prime components. We have our Cn prime. We have a hyperbolic sine of k sub n prime b. And now we have our, I'm going to write this down here. These are just still multiplied on. We'll have our sine of k sub n prime y. And now we have this thing that we're multiplying on, which is sine of k sub n without the prime y. Yeah, you may want to watch the video for 3.16 as well. It's very similar, and maybe I don't stumble over the words as much in that one. I don't remember. Did that one a long time ago. So Fourier's trick, what this does is it exploits the orthogonality between these two sine functions. So as we integrate over this, if n prime is not equal to n, then the integral will go to 0. It's kind of like a Dirac delta function. So n prime has to be equal to n if we don't want this integral to go to 0. So what it does is it, just like Griffiths says, it picks out the one value out of this infinite sum where n prime is equal to n. So that way we can get rid of this infinite sum, and all the n primes can go away, and we'll just be left with these n's. That's why I went and put this this prime on. Oh, excuse me, I'm out of the picture. That's why I went and put this prime on these ones, because I want the primes to go away and be left with the n's. So our left-hand side here is still going to be the same. Keep in mind that k sub n is still equal to this n pi over a. And for the right-hand side, Fourier's trick has killed off this whole infinite sum. And so now, everywhere we see an n prime, we can put in an n. All right. So, yeah, let's go ahead and we'll write out the integral thing as well. Okay, we have a Cn, again an n, not an n prime. We're setting them n prime equal to n. Sorry, this is separate. Okay, we have our sine, our hyperbolic sine of kn b. And then we have this part right here. And these two can now multiply together because the n prime, for another, once again, the n prime is equal to n. All right. So let's write this out a little bit better, because we see that these pieces right here actually do not even depend on y, so they can come outside the integral. And we're left with an integral from 0 to a of sine squared k n y. This integral gives us, let me double check it, it gives us an a over 2. I'm not going to go ahead and do that integral because it will just take more time. This video is already way too long. All right. So, what do we have now? What we were trying to solve for is the Cn. Okay, let's go ahead and solve for it. I'm going to bring this a over 2 over to the other side, so now it's a 2 over a. And we'll divide by this hyperbolic sine. Okay, and now we just have this integral. Right, so again, I'm solving for this right here, which I bring here, and then I'm bringing these other things to the other side, and now we just have this part to worry about. 0 to a of v y sine of this k n y dy. So what we've just done is we've solved for this coefficient. We've solved for, you know, back when we were asking the question of our potential right here, we wanted to know what coefficients do we plug in every time we see, you know, this is the part of the potential that we don't know. So now we do know what it is. It's not pretty, but if we knew what this v naught y was explicitly, and you ask, you know, for n equals 3, what is Cn? Then we could solve this equation right here and find it. So we have actually determined the entire potential. Dare we write it out? I don't know. I don't think it would take a lot of space to write it out in all of its glory, because it would be this right here. We would plug in this for every time we see a k sub n here, and then for c sub n we would plug in this, and again there's k sub n's in this one too. All right, so we could write it out, but it's probably more instructive to just look at this right here and just picture this huge Cn thing plugged in right here, and every time you see a kn, picture this n pi over a plugged in. So that is the potential. So that's the solution to this problem. Now, Griffiths does say that we should solve it for, suppose that v naught is not a function of y. All right, so it's not a function of y, it's only a constant. So basically suppose that the side of the rectangular pipe here doesn't depend on y. It's just a constant potential V naught. All right, it's not grounded, so it's a different potential from the other three sides, but it's constant along this side. In that case, what do we get for our Cn? Well, we still have this 2, and this V naught can now come out of the integral because it's a constant. We have an a, we have a hyperbolic sine of knb, and then we just have an integral from 0 to a of sine, excuse me, was this squared? No, this is just, yeah, this is not squared. This is just sine kny dy. All right. So now, let's run through this really quick. We have our Cn 2v naught over a hyperbolic sine of knb, and then we will get a 1 over k n. We have a minus cosine of kny. This multiplied by that, and now we are evaluating it from 0 to a. So at 0, this is going to give us a minus 1. In fact, we can just take this minus sign and flip the limits. Let's write this out. I'll write this kn over here, and then what we have is so a cosine at 0 gives a 1, and a cosine at kna gives us either a +1 or a -1, because remember kn is equal to n pi over a. So multiplied by a, that just gives us an n pi. So for even, let me write this as a plus or minus 1. For even n, which includes 0, we will get minus. Is that correct? Yes. We get the minus sign here. Why do we get the minus sign? Because we're subtracting off the integration, the limit of integration. I should have written out more steps here, but what I did was I made this a plus, and then I made this an a down here and a 0 up here. So this 0 cosine gives us this 1, and then we have a minus cosine of of n pi. So so for even n, we would get a minus +1, which is a -1. And then for odd n, we get a plus. So for even n, when we get a minus sign here, 1 minus 1 is 0. And so Cn equals 0 for even, that's an R, for even n, which tells us that, you know, if Cn for even n, remember Cn is, where did it all go? Somewhere here. Cn is multiplied by this whole term, right? There's nothing added on or anything beyond what's in this sum. So that tells us that V equals 0 for even n. That doesn't, yeah, that doesn't make, but basically there's only odd terms in our sum. So only odd n. in our sum will survive. What do we get when for odd n? Well, 1 plus 1 is 2, and that 2 will multiply with this 2 and give us a 4 v naught over a, I'll put in this k sub n here, hyperbolic sine of k sub n b. So now, one final page to this whole mess. So for v naught constant, we actually get an answer of v it's this right here, except we're going to go ahead and plug in the c ends now, and we're only summing over the odd ends. So I write my n equals 1, 3, 5, dot, 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 out to infinity. And now I'm going to use this Cn, right, for v naught. I'm just going to leave the k's in, right? I could write that out explicitly, but I'm lazy, which is why we just went through 15 pages or something of algebra and calculus and stuff. So this Cn, right, we're plugging that in. Okay, now we just multiply by these. K sub n x and a sine, normal sine, of k sub n y. And just a reminder, since I left these k sub n's in, k sub n is equal to n pi over a. This is our final solution for when v is equal to constant.